Welcome back to the deep dive.
Huh.
Today we're diving into, well, a really fundamental concept in physics, the renormalization group and critical phenomena. Have you ever watched water boiling and seen how it gets kind of cloudy and turbulent right at the point where a liquid turns to steam?
Mhm.
Or maybe looked at weather maps, seeing these huge storm systems with swirls within swirls,
Yeah, those everyday things, they actually point to a really deep scientific puzzle.
which is,
Well, the challenge is, how do you get a handle on systems where the little fluctuations, the tiny variations, don't just average out, they actually persist. And they're important at every single scale you look at.
from the tiny atomic level all the way up to the global.
Exactly. Think about turbulence in the air. You've got massive eddies, thousands of miles across, right down to millimeter-sized swirls. It's the same structure repeating.
Wow.
Or even, within fundamental particles. Quantum field theory suggests things like electrons or protons, which we think of as basic, might have this complex internal structure that just keeps going smaller and smaller.
So trying to model that, say, the atmosphere, you mentioned needing something like 10 to the power of 25 grid points. That's
Yeah.
just astronomical.
Completely beyond us computationally. And our usual math tools, our analytic methods, they just get swamped by what we call very many coupled degrees of freedom.
Yeah.
Everything affects everything else across all scales.
And then you have these critical points, which sound even weirder.
Oh, they are fascinating. Take water again. If you crank up the pressure and temperature way up, like 218 atmospheres and 374 Celsius, you hit its critical point.
And what happens there?
The difference between liquid water and gaseous steam just
Okay.
vanishes completely.
Well, liquid.
Instead, you get this weird mix of water-like and steam-like bits constantly shifting with structures appearing and disappearing at all sizes, from microscopic upwards. And this mixture scatters light like crazy, making the fluid look milky, opaque. That's called critical opalescence. It happens because the usual forces that make small drops or bubbles collapse just disappear at that point.
Okay, so the challenge is huge. Connecting the micro to the macro when every scale in between matters. How do we even start?
Right. And that's where this idea, the renormalization group, or RG, comes in. It's a really clever strategy.
So our mission today is to unpack that, figure out what the RG actually is, how it works, where it came from, apparently quite a story there, and what it's used for.
So good?
Let's start with the basic idea then. How does RG approach this scaling problem?
Okay, so the core idea of RG is to tackle these multi-scale problems bit by bit, sequentially.
Ow.
You basically integrate out, or average over, the fluctuations scale by scale. You start at the smallest, say, atomic scales, figure out their collective effect, and then use that result to describe the system at a slightly larger scale. Then you repeat.
So it's like zooming out, blurring the finest details progressively.
Exactly like zooming out on a map. You handle the complexity one length scale at a time, simplifying as you go.
That sounds very different from the older ways of thinking about these things, like Landau's theory.
Oh, absolutely. For a long time, Landau's mean field theory was the standard approach, especially for things like phase transitions.
Like in a magnet.
Yeah, perfect example, take a ferromagnet, like iron. Below a certain temperature, the Curie temperature, Tc, it spontaneously gets magnetized.
Right.
Now, right near Tc, that magnetization, let's call it M, it vanishes in a specific way. Experiments show it goes like TTT, raised to some power, beta. And beta in 3D is about 13.
Okay.
And there's another key quantity, the correlation length, ET11. That's roughly the distance over which the little atomic magnets are aligned. This length becomes infinite at Tc. Just above Tc, it shrinks, going like 2dc to the power of minus nu. And nu is experimentally around 23.
So those are the experimental numbers, 13 and 23. What did Landau predict?
Well, Landau's theory made a big assumption. They basically said, those microscopic fluctuations, they'll just average out. They aren't important for the big picture.
Okay. Seems reasonable.
It seems reasonable, but it's wrong, at least in dimensions we care about. Based on that averaging assumption, Landau predicted beta 12 and nu x12.
So 12 and 12, but experiments say 13 and 23. That's quite different.
It's a major disagreement. And it turns out Landau's theory is only really right for systems in more than 4 dimensions.
4 dimensions? Why 4?
It's a kind of critical dimension. Below 4 dimensions, those long-range fluctuations that Landau ignored become dominant near the critical point, and they completely change the behavior. They break the mean field approximation.
So that averaging idea just doesn't work. And this connects to another puzzle, right? How can these smooth interactions at the atomic level lead to such sharp, non-smooth behavior, what you called non-analytic, right, at the critical point?
Exactly. That was a deep conceptual problem. Landau's theory, being built on smooth functions and averaging, struggled to explain these sharp corners, these non-analytic power laws like beta and nu, emerging from seemingly well-behaved microscopic physics, especially when you consider an infinitely large system, the thermodynamic limit.
Hmm.
How does summing up infinite smooth things give you something non-smooth?
Okay, so that's where the RG really shines. It handles those fluctuations.
Precisely. RG embraces those long wavelength fluctuations that Landau ignored, and the way it does it is revolutionary. Remember the zooming out, integrating scale by scale.
Yeah.
As you do that, you keep generating a new, sort of effective description of the system at each larger scale. Now, here's the clever part. If you write this description in a special dimensionless way, getting rid of units like energy or lengths, just pure numbers, you find that the mathematical rule, the transformation that takes you from one scale to the next, looks the same every time you apply it.
It repeats.
It repeats. And as you keep applying this transformation, zooming out further and further, which is like getting closer and closer to the critical point where the correlation length is huge, this mathematical description of the system, this free energy functional, it flows towards a stable state, a fixed point.
A fixed point, like it stops changing.
Exactly. It reaches a form that doesn't change anymore under further steps of this scale transformation. Think of it like a river flowing towards the sea. The river might start in different mountains, but they all end up flowing into the same ocean. That ocean is the fixed point.
Okay. And what does that mean for the physics?
It means that the behavior right at the critical point, which is governed by this fixed point, is independent of all the messy microscopic details you started with.
Wait, really? The details don't matter?
The specific details of the atoms or molecules? No. This explains this amazing phenomenon called universality.
Universality.
Yeah, it's why completely different systems, like the liquid-gas transition in water, the magnetic transition in iron, even transitions in metal alloys, why they all experimentally show the exact same critical exponents, like beta and no.
So that 13 and 23 isn't just for magnets.
Nope, it's the same for fluids near their critical point, too. It's because, deep down, near criticality, they are all described by the same fixed point interaction. The RG flow washes away the irrelevant microscopic differences and reveals this underlying universal simplicity.
Wow. That's a really profound idea. And RG could actually calculate these exponents better than Landau's 12.
Yes, especially using a trick that works near 4 dimensions. It's called the epsilon expansion, where epsilon is just 4 minus the dimension, d.
Okay.
Near d4, the fixed point becomes simple enough to analyze mathematically. Wilson and Fisher used this to calculate exponents like beta and nu as a series in epsilon. For D3, so epsilon 1, they could get values like nu around 0.6, much closer to the experimental 23 than Landau's 12.
So it wasn't just a conceptual breakthrough, it gave actual numbers.
Right. It showed that these exponents weren't just simple fractions like 12, but could be complicated, non-trivial numbers that depended on the dimension, and it gave a way to calculate them. That was huge.
And the history of how this all came together is pretty interesting, too, you mentioned. Not a straight path.
Not at all. It's full of twists. I mean, you had early theories by van der Waals for fluids and Weiss for magnets back around 1900, which were basically mean field theories.
Right.
But even then, careful experiments were starting to hint that the critical exponents weren't quite matching those simple predictions. The puzzle was simmering for decades.
Then Onsager came along.
Yes, Lars Onsager's exact solution for the 2D Ising model in 1944. That was a bombshell.
Why?
Because it was an exact calculation for a non-trivial model, and it gave exponents, like nu1, that flatly contradicted the mean field prediction of nu12. It proved mean field theory wasn't the whole story.
So that really forced people to look beyond averaging.
Definitely. Then in the 50s and 60s, you had a whole bunch of brilliant people, Dom, Sykes, Fisher, Wyndham, Kadenoff, plus crucial experimental work developing new tools. They used things like high-temperature series expansions, basically calculating properties term by term, and they developed scaling laws, phenomenological relationships between the different exponents. They were building the framework, seeing the patterns, but the deep underlying reason why these patterns existed was still missing.
And the key insight came from quantum field theory. That seems like a leap.
It does, but that's where Kenneth Wilson came in. His background was in QFT, dealing with these pesky infinities that popped up in calculations like in quantum electrodynamics, QED.
The theory of electrons and light.
Right. Physicists like Bethe, Schwinger, Feynman, Dyson had developed renormalization back in the late 40s as a way to tame these infinities. It involved absorbing the infinite parts into a redefinition of basic parameters like the electron's charge and mass, leaving finite measurable predictions.
Okay, so renormalization was about handling infinities in QFT.
Initially, yes, but the term renormalization group actually first appeared in 1953 by Stueckelberg and Peterman. They noticed there was an ambiguity, a freedom, in how you did this redefinition, and the group described how physics stayed the same under these different choices.
Uh-huh.
Then, crucially, in 1954, Murray Gell-Mann and Low took it further. They considered how the effective strength of the electromagnetic interaction, the effective charge of the electron, seemed to change depending on the distance scale, or equivalently the energy scale you probed it at,
The charge isn't constant.
not the effective charge you measure. They showed it varies logarithmically with the momentum scale, lambda, and derived the differential equation describing this change. This idea of a scale-dependent coupling constant was a huge inspiration for Wilson.
So Wilson took these ideas from QFT. How did he connect them to boiling water and magnets?
His breakthrough came while trying to simplify a different problem in particle physics fixed-source meson theory. He had this idea: instead of dealing with all possible momentums continuously, what if you just considered momentum in slices or shells?
Like frequency bands.
Exactly. Deal with the highest momentum slice first. Figure out its effect, effectively integrate it out, and see how it modifies the interactions for the next lower momentum slice. Then repeat.
Ah, so it's the same step-by-step elimination, but in momentum space instead of real space?
Precisely. And when he did this, he made a startling discovery
Which was?
that even if you started with a simple initial theory, this process of integrating out momentum slices generated an infinitely complicated effective theory at the next step, with potentially infinitely many different types of interactions, or coupling constants.
Infinite interactions. That sounds worse, like you're making the problem harder.
It sounds terrifying. Everyone assumed physics should be described by just a few fundamental interactions. But Wilson showed that, crucially, if you chose the slices correctly, the effects of all these newly generated complicated interactions could be systematically controlled. They were boundable. This freed him from the constraint of thinking only a few interactions mattered. RG could handle the complexity.
Wow, okay. And Kadanoff had a related idea around the same time.
Yeah, independently, in 1966, Leo Kadanoff proposed his block spin picture for systems near criticality.
Block spins.
The idea was, if the correlation length is huge, maybe you can group blocks of many atomic spins together and treat each block as a single new effective spin, interacting with neighboring blocks via some new effective interaction strength at a new effective temperature.
So it's another way of coarse-graining changing scale.
Exactly. It provided a very intuitive picture and another way to derive those scaling laws, showing how the problem could look similar at different scales. It meshed perfectly with Wilson's more formal momentum space approach.
And then the final piece was realizing it's simplified in 4 dimensions.
Right. In 1971-72, Wilson, collaborating with Michael Fisher, had the crucial insight that the fixed point governing the critical behavior became particularly simple right at d4 dimensions. This allowed them to use that epsilon expansion, epsilon 4d, to systematically calculate exponents for dimensions near 4, including our physical d3.
You can get those numbers like nu epi 0.6.
And get those numbers, finally bridging the gap between theory and experiment for critical phenomena. It was a triumph.
So after 1972, with Wilson's work and the epsilon expansion, things really took off.
Oh, absolutely. It was like a dam breaking. Suddenly, there was this powerful, systematic tool. People started calculating exponents for all sorts of systems in 3D with amazing precision, mapping out how critical behavior depended on dimension, symmetry, number of components. It unified the whole field.
But it didn't stop there, right? The applications went way beyond just critical points.
Far beyond. One early success was the Kondo problem. This is about how a single magnetic impurity atom behaves when embedded in a non-magnetic metal at very low temperatures. It was a really tough, long-standing puzzle in condensed matter physics.
RG solved it.
Wilson used RG ideas to get the first accurate calculation of its behavior, particularly the magnetic susceptibility at 0 temperature. It was later confirmed by exact mathematical solutions, but RG got there first, showing its power for strongly interacting problems.
Okay, that's cool. But then, QCD, quantum chromodynamics. How does RG apply to quarks and gluons?
This is where RG becomes truly central to fundamental physics. In the early 70s, Gross, Wilczek, and Pulitzer used RG to study non-abelian gauge theories. the kind of theory QCD is.
And they found
They discovered something amazing: asymptotic freedom.
asymptotic freedom means.
It means that in QCD, the strong force coupling, how strongly quarks and gluons interact, gets weaker at shorter distances or higher energies.
Weaker, that seems backwards, like gravity or electromagnetism gets stronger when you get closer.
Exactly. It's totally counterintuitive. But it means at very short distances, quarks behave almost as if they were free particles. This brilliantly explained results from experiments in the late 60s called deep inelastic scattering, where high-energy electrons were shot at protons. The electrons seem to be scattering off nearly free point-like things inside the quarks.
So that's why quarks look free inside protons?
At high energies, yes. But the flip side of asymptotic freedom is that the coupling gets stronger at larger distances, at lower energies.
Ah, so that's why you can't pull a single quark out of a proton. The force gets incredibly strong.
Precisely. It leads to confinement. RG explains both ends of this behavior, why quarks seem free when probed hard, but are permanently bound inside hadrons at normal energies. It's a cornerstone of our understanding of the strong force.
That's incredible, and RG is used in other fundamental theories, too.
Oh, yes. Lattice gauge theory, which is our main tool for calculating things in QCD numerically, is fundamentally based on RG ideas. Discretizing spacetime is like the first step of an RG transformation,
Uh-huh.
and it's absolutely essential for grand unified theories, or GUTs. These try to unify the strong, weak, and electromagnetic forces into a single force at extremely high energies.
How does RG help there?
RG allows you to calculate how the strengths of these three forces change with energy. Remarkably, when you extrapolate using RG, the three coupling strengths seem to converge to become equal at a fantastically high energy scale, around 1015 or 1016 GeV.
Suggesting they really might be unified way up there.
Strong circumstantial evidence, yeah. It suggests the apparent differences between the forces we see are just low energy effects, and the underlying unity only reveals itself at unification scales. RG is the tool that lets us bridge those vast energy gaps.
Wow. What about other complex systems, like
Uh,
turbulence or chaos?
Turbulence is, well, it's still one of the great unsolved problems. People have tried applying RG ideas, and there's been some progress, but a full RG theory of turbulence remains elusive. It's incredibly hard.
But chaos.
There, RG had a spectacular success. Mitchell-Feigenbaum in the mid-70s discovered universal patterns in the transition from regular behavior to chaotic behavior in simple dynamical systems. He used an RG-like approach to explain why certain numbers, like the rate at which period doubling bifurcations occur, are universal, independent of the specific system.
So universality pops up again.
It does. It seems to be a really deep principle in complex systems.
Are there new ways of using RG now? Modern techniques?
Definitely. Computationally, a very powerful technique is the Monte Carlo Renormalization Group, or MCRG.
Monte Carlo, like
Yeah.
random sampling.
Yeah, combined with RG ideas. You simulate the system on a computer using Monte Carlo methods, then you perform RG transformations numerically on the configurations you generate. It allows you to directly extract critical exponents and scaling functions without needing analytical tricks like the epsilon expansion. It's very accurate, especially in 2D, and becoming increasingly powerful in 3D as computers get faster.
So looking forward, where else might RG make an impact? It feels like the possibilities are huge.
They really are. I mean, this work, extensive as it is, feels like just scratching the surface in some ways. People are thinking about applying RG ideas to develop better, simpler, effective theories for things like the chemical bond.
Instead of solving the full quantum mechanics every time.
Yeah, exactly. Find the essential degrees of freedom for chemistry. Or understanding QCD better at high energies and densities, which is crucial for interpreting results from particle colliders like the LHC.
And maybe more practical problems.
Absolutely. Things in material science like percolation, how fluids flow through porous rock, frost heave, why ground swells when it freezes, even crack propagation in solids. These all involve complex physics happening at microscopic scales that determines the macroscopic behavior. RG offers a potential framework for understanding and predicting these technologically important phenomena.
So wrapping this up then, the renormalization group isn't just one technique, it's more like a whole way of thinking.
I think it's a great way to put it. It's a profound conceptual framework for understanding how systems behave across different scales. It teaches us that the essential physics governing behavior at one scale can emerge from and simplify the description at a smaller scale.
It's about finding the connections, the nuggets of knowledge, as the outline put it, that persist across scales.
Exactly. It reveals this hidden structure, this way of organizing complexity by focusing on how descriptions change as you change your viewpoint, your scale of observation. It finds the universal patterns beneath the surface details.
So for everyone listening, maybe the takeaway is to think about where else you see this kind of scaling. Patterns repeating, maybe simplifying as you zoom in or out.
Right. It could be in ecosystems, economic systems, social networks, maybe even just how ideas spread.
Thinking about how small actions scale up or how different complex systems might actually share some underlying organizing principles.
hmm The RG gives us a powerful lens. It suggests that sometimes understanding complexity isn't about knowing every single tiny detail, but about understanding how those details relate to each other across scales. How does the micro build the macro? It's a question that goes far beyond physics.